Yes, thank you very much, Vincent, for the nice introduction. I hope you see the good side of the slides now.
Yes, it is.
Yeah, so indeed, I did my postdoc in the Netherlands with Maria Loy, and last year I joined some Stranks lab here in Cambridge, and I thought I'll present something about all the work we did on spectroscopy and microscopy of these two-dimensional perovskites. Given that, as far as I understand it, this is the first talk on 2D perovskites in the series, this gives me an opportunity to first also promote some of the nice work done by other people in the field. And I think it's always interesting to stress that, of course, everybody when working on perovskites always has the solar cells in mind and this boom of solar cell efficiency that we saw over the past decade. But actually, the 2D perovskites, they didn't really come from the 3D perovskites. So obviously, a lot of us now went into that area due to the solar cell research. But it was already in the late 80s of the previous millennium that, let me just get my pointer here, that people started working on them for spectroscopy first, late 80s. And then there was also a nice paper by Cherry Kagan and David Mitzi in 99 on the field effect transistors on the tin-based perovskite, actually. Very often, you find the term natural quantum wells or something similar when referring to these materials. This is basically because we have our regular metal halide octahedra, and they are sandwiched between rather long organic spacer cations. So different to the limitations that we know from the 3D perovskites, where these cations have to be very small. We can actually use bulky materials or bulky cations and then impose a two-dimensional electronic structure. This, of course, creates a confinement, both a carrier confinement or quantum confinement and a dielectric confinement. And these materials are actually excitonic in nature. So we don't have free charge carriers anymore as we like in our solar cells, but these form correlated electron hole pairs. What most of you are also familiar with is this is the case of a really ideal two-dimensional perovskite. We can also mix it with the 3D phases and then create what we now call the quasi-2D perovskites, where we actually have several inorganic octahedral layers sandwiched between these organic spaces and then call them n equals 2, n equals 3. And we somehow lift the confinement a bit, change the energetics, the area of the absorption and the emission, for example. And of course, these materials are used in a broad variety of optoelectronic applications. Solar cells, I mentioned already, so as interface layer, extraction layer, for example, sometimes also as a really 2D, 3D mixture, often because they seem to be more stable, but rather recently, especially, some of these organic spaces have been nicely used to boost the performance, just to extract carriers. Just a few of these organic spaces on top seem to be very beneficial for the energetics. And then we can go through the entire field of scintillators, photodetectors, and given that they are so very, or they have large excitonic binding energies, the field of spintronics and polaritonics, broad playing field for physics. And eventually, of course, light-emitting diodes, because they're so bright. Good. I will not actually talk about devices today. It's all just spectroscopy, microscopy. Let me just add one more introduction slide. You can use your knowledge from the 3D perovskite to understand a lot about the energetics of these 2D perovskites. Again, we can, looking at these metal halide octahedra, use tin or lead, and then we can use bromide, iodide, and chloride. Mixing them if we want to. We can also create the double perovskites if we want to. So we have basically the entire toolbox from the 3D perovskites and can use it here as well. And again, our band gap, the fundamental band gap is mostly determined by the metal and the halide. So if you look at something with lead iodide compared to something with tin iodide, it's the tin that really changes the band gap energy. You change your A side cation, there's hardly any difference here in the band gap energy. There's a bit of difference which can be explained by basically distortions of these inorganic octahedra. So if you put something very long, something very bulky in here, the electronic structure will change a little bit, but this is not due to hybridization of the electronic states. For example, if you see this metal halide metal bond here, or angle, sorry, and for very large for the distortions, or if you see the distortion here, you change a little bit band gap energy, but it's mostly the halide in this case that really determines what you observe. Now let's look at some of the data I took in cooperation with others, of course. I will, in the first part, only stick to a system with prototypical PEA organic spacer. It's just an amine head group, and then there's a bit of a benzene ring and alkyl chain in between. And here you see different compositions. We varied the metal and the halide here, and the white light, you can already see the different absorption, so different color. And the excitonic absorption here is a narrow peak, and then at higher energy, all of them show continuous transitions, or the transitions from the continuum, to be precise. Analogously to the 3D perovskites, when we use bromide and go to iodide, we shift it to the green, and then if we exchange lead for tin, we go to the red. Now let's use UV light, and you can see that these materials actually exhibit very bright and nice colors. So red, green, and blue emission. That's of course very nice if we think about RGB applications. We want to use them in LEDs. Also, it's not just nice that we have bright colors, but they're also narrow emission lines. So that's again a very nice benefit of these materials. What I would like to focus on, however, is this curious case of the lead chloride variant. And if you think that with bromide, we are already at the edge of the UV region, 3 UV in absorption, and you see the PL here that looks pretty wide. That should be non-visible to us, right? It should be in the UV. And actually it is, but it also isn't. If you look at the absorption here on the right, you see that the excitonic transition of the absorption is really at 3.6 eV in the UV. There would also be, this is the photoluminescence, a PL peak, but our detector isn't sensitive anymore. But we know from the literature that there is. But there is, in addition, a very broad emission band over the visible range, peaking at 2 eV, or around 600 nanometers. So this creates our white light in this thin film sample. And I would like in the following few slides explain why I think this white light is generated in these films. So on the origin of the broad emission. We actually observed that before already in a different material system, and this is in the lead-based system, but here we were looking at single crystals. And we had a synthesis batch where we observed in lead iodide both this narrow emission peak from the free exciton and the broad emission peak shifted towards the red at lower energy. And when we observed that, we were a bit puzzled. But looking at the literature, there were actually quite a few reports out there on similar, not the same compounds that observe very broad emission bands over the visible range and accordingly white light emission. The explanation in the field was that this was due to self-trapped excitons. Now, this might not be a concept to which all of you are familiar, or with which all of you are familiar. So let me just explain that in a nutshell. A self-trapped exciton is more or less analogous to a small polaron. If you have an exciton that moves freely, but at the same time interacts very strongly with the lattice, it might be so strong an interaction that the lattice is deformed and leads to a collapse of the correlated electron wave functions. So the exciton self-traps. Often is this is shown in such a configuration coordinate model where you see a ground state, your exciters, that would be the free exciton, but this reorganization, so change of the configuration coordinate, allows for the exciton to go into a lower energy state. And then accordingly, if this now recombines radiatively, it's redshifted. The important part here is that this is an intrinsic material property. Either you have self-trapped excitons or you do not. And if you have them, there might be temperature dependence. You can see there is often a trapping barrier and a detrapping barrier. but it should be more or less constant if you look at the same temperature. The other thing I would like to underline that this is a transient effect. So there's no state within the band gap. The self-trapped exciton only exists when you excite the material. So then you might understand my confusion or our confusion when we looked at some of our single crystals a bit more closely. So this is now a wide field microscopy image. We put the crystal in a microscope, illuminate everything with a blue laser, and then we take a picture. And you can see that one of these crystals now, I call that the green flake, is completely green, and the other one is completely red. And now these are the extreme candidates. There were also a lot of them in the middle, of course, that were more or less orange, but there was a flake-to-flake difference. And as I just said, self-trapped excitons should not show such a variation. So we looked a bit more closely with a confocal laser scanning microscope. So here we basically raster scan the single crystals or the flakes, and then we measure the photoluminescence point by point, generate these images, and we actually just scan through two different channels. One of them that is just sensitive to the green light from the free exciton, and one of them the red light of this broad emission. Here you can also see if we go to different areas and take the spectrum, how we cover these two different spectral areas. So, and what should immediately be clear here is that we have, for example, this area A and this area B. In A, we have very strong green emission, the free exciton, and in area B, we have weak green emission, but very strong red emission. In other words, this strong broad emission coincides with a very weak narrow emission. There seems to be some sort of trade-off. We can add to that by also looking at the time-dependent photoluminescence. So just going to one spot and measuring the decay. And here now we look at the narrow emission only. So just high energy. And you can see in green, one of the regions where there's hardly any broad emission or no broad emission, and we have a much longer lifetime than in a region where there is strong broad emission. In other words, this narrow emission or the broad emission is a loss process for the narrow emission. Finally, if we expose the flakes for a long time with our blue laser, you can see that the broad emission intensity really is reduced over time. There's also a bit of change in the narrow emission, but it's not so severe. So it is not constant, whatever is giving us this broad emission band. All data actually point away from self-trapped excitons. So what is our rivaling hypothesis? Many of you that work with devices probably thought of this already initially. It could just be a trap. It could be a distribution of trap states. It could be a deep trap state, or just donor acceptor transitions. Many possibilities that could give you a redshifted emission that could also be broad. And actually, if you look at the literature and compare or comparable systems, for example, zinc oxide or gallium nitride, both form excitons, both are very polar lattices. There you see similar photoluminescence spectra, right? A narrow emission band and a broad emission band. And there everybody refers to some sort of defect state, either vacancy, interstitial, or an impurity. Nobody invokes a self-trapped exciton to explain it here. So can we prove that actually? We think we did, and we did the following. Rather than exciting the material above the band gap with a blue laser, where you observe both the narrow and the broad emission, we used excitation lasers with a low energy, or with low energy photons, to directly excite the state within the band gap, which we proposed was there. And we should only observe the broad emission. Now, if we detune that from close to the band edge, far away, then we lose a lot of the PL intensity, but we can still observe it. Now, one thing we need to exclude is these 2D perovskites, they're notorious for being good absorbers for two photon processes. So it could be we use small energy photons, but we might still excite above the band gap. This can be excluded by just looking at the dependence of the PL intensity upon the incident power variation. And that you can see here for two different organic spaces, PEA and just a fluorinated version. We can excite the broad emission with low photon energies, and it scales linearly. There is a state that we can directly excite with one photon. And actually, if we go to even lower energies, photon energies, that is, we really need to power, or we need a lot of power with a femtosecond laser, for example, and then it scales quadratically. So you need two photons, but then it's this state, this process. The slope here is nice, or nicely allows you to distinguish between those two. Okay, so I hope that convinces you that these are defect states. The question is then, what kind of defect state? Back when we looked at it the first time, we thought since the broad emission changes with extended illumination, this is probably related to halide defects. We know the halides, they diffuse around, especially when you shine light on them. And we also, in a different story, we looked at differently synthesized materials or differently synthesized thin films by just varying the precursor ratio, PEA iodide and lead iodide. And by varying this precursor ratio, we saw that we could suppress, to some degree at least, this broad emission at room temperature. So it shouldn't be pollution, no impurity. It should be some form of intrinsic defect, again pointing towards probably a halide-related defect. Other works in the field came to similar conclusions at that time. So iodine vacancies have been proposed. There was also a previous report that proposed iodine interstitials. And there were also, however, some reports that claimed we might be looking at so-called extrinsic safe-trap excitons. A bit of a longer story what this really means, but there is a difference generally to defect states. Just to keep you open-minded, we nonetheless think it's due to the halide defects, and we actually looked at other systems afterwards. What you see here on the left is the overview spectrum of PEA tin iodide, the lead iodide, and lead bromide, but at low temperature. What we observed when looking at the flakes was that when cooling down even the green flake, it would become red. So this broad emission is observable at low temperature. It's still there, even if, for example, if you have a flake that doesn't have a lot of defects, you don't see it at room temperature. So it's there in bromide, it's there in iodide. Tin is a bit of an interesting case. We might see it here as a little shoulder, or we cut it off. We now work on or collaborated with some theoreticians, and we know we actually cut it off. So there is something in the tin here as well. And what their data points to is that these are actually halide vacancies in all these compounds that govern the broad emission bands. It's work we're just currently wrapping up. Just to extend, it's not the PEA ligand that is somehow special. In this PDMA system, it's a different type of organic spacer that I'll show you in 2 slides. We see the same broad emission band. So it's really the metal halide that determines this broad emission at low temperature. Good. So far for the first part, this was broad emission bands, then 2-dimensional perovskites, defects, and it was all explained in a model that assumed we had some sort of homogeneous material. And microscopy obviously helped very much because the flakes were small, and we could nicely observe that in the flakes there were no effects from the facets, for example. It was the entire flake or different regions of the flake that either showed a lot of defects or few defects. Here now I would like to highlight a story that really tells you why when we are looking at some of these systems, it's very important to consider heterogeneities, variations at a local scale. We cannot just look at a sample macroscopically and assume it was one kind of semiconductor. And this is the so-called PDMA system. PDMA is just a different spacer cation, PDMA 2+ here. It's a similar benzene ring, but it actually has two of these functional groups. So two amine groups on opposite ends. And very often you will find in the literature that these compounds are then referred to as Dion-Jacobson compounds, while the other ones are just monoamines. They are referred to as Robertson-Popper compounds. Why are we interested in these materials? Well, there's actually a very good argument from solar cells, or just from devices in general. Since they have two functional groups, you only need one spacer cation to create your two-dimensional material. So the distance between the inorganic layers might be reduced, and therefore you can really promote the transport across these layers, or at least we think you can enhance the transport across the layers. And there is a stability argument here between the two spacer cations. You obviously have van der Waals gap, and there might be a benefit by just deleting, erasing, getting rid of this gap and having these ionic interactions in between the inorganic layers. Good for us. Again, we just looked at the pure two-dimensional case of PDMA and lead iodide in this case, and we wanted to start by just understanding what's the difference for the photophysics. They look so similar, but then again, there's the second functional group. And if you look at room temperature, the photoluminescence, as you would expect, is actually at a similar peak energy, right? Again, your band gap is determined by the metal and the halide. That's unchanged. And then we have a bit of a distortion in the system that can create a bit of a difference in the band gap energy. However, you can also see that this PDMA system shows you much broader PL width. And looking at time-resolved PL at room temperature and also some degradation, or at least longer exposure of the sample to the laser, suggested that there was something of a shoulder in here, so that there might be two emitting species already at room temperature. So, and if things overlap at room temperature, when things are hot, you might be able to resolve it when you go down to colder temperatures. And this I show you here. You can again see normalized PL as a function of the energy. In blue, the PEA lead iodide. We know already there are distinct peaks in the system. I labeled them X1, X2 here, and there's a whole discussion of what this means. There could be triplet states, dark excitons. There could be bound excitons. I'm going to skip that discussion a bit today, but usually what I would like to highlight is that when explaining these transitions, we're usually referring or conceptualizing that as one semiconductor. And then there are some states in the semiconductor, for example, due to a biexciton or due to the triplet. It's one material. The PDMA, in contrast, does not show these narrow emission bands, really. Right? It's all still very broad. Things seem to be overlapping. More interestingly, though, is if we go to different sample areas, you can see this here, just measured in 5 different spots, the spectra are completely different. We seem to have some subpeaks here and here, around 2.36 and 2.35 eV. And then there's also a shoulder here, but there's a huge spot-to-spot variation. So in other words, there's a huge heterogeneity in the low temperature photoluminescence. This allows me to make the segue again to microscopy. So if there's such heterogeneity, we would like to really look at it a bit more in detail. And you can see that one of such images here. So we performed the same confocal experiment where we scanned over the sample and measured the photoluminescence through our 2 different channels. I'll just show you the red channel here because it shows you the nicer contrast. And what you can observe here is that well, broad areas are actually pretty light. There's a lot of intensity here, but then there are smaller areas that are pretty dark. And actually, it's not just the areas, it's distinct grains. So you have a type of grain that I labeled with 4, 5, 6 here that are dark in the broad emission region, and then there are a lot more grains that seem to be bright in the broad emission range. And we can actually go to distinct spots here and take the spectrum again, or the spectra again. This is where the 1, 2, 3, 4, 5, 6 comes from. And we observe actually distinct spectral changes. However, not just in the area of the broad emission here, 1, 2, 3 versus 4, 5, 6, but we also observe it around the narrow emission here. There's a 10 or actually 12 MeV shift around the narrow emission band. So in other words, when we look at the macroscopic PL here, and we see all these subpeaks in our PL spectra, this is not because there's one material and there's one, let's say, bound exciton or a dark exciton in here, but there are distinct properties of distinct crystallites. So at least 2 types are available here. At the point of, when we looked at this first and we published that last year, we proposed that this was due to defects, so certain crystallites having more defects than others and a certain type of defects. However, there was also a type of or a line of literature that proposed there might be differently stacked inorganic layers in here. So usually you have the layers stacked parallel to your substrate surface. They could also be stacked vertically. We didn't see anything in XRD, so we favored the former, couldn't, however, really exclude the stacking. In some follow-up work that I've been doing now during the last year, I think we can now be pretty confident that it's not the stacking itself. We used hyperspectral microscopy to really look in detail into the different emission or locally resolved emission. Let me just highlight what, briefly scheme out what we did here. Usually we take one picture of the entire PL and then we maybe can use a filter to narrow it down to the broad emission or the narrow emission. But obviously the nicest thing we could do would be to get the microscopy image of the PL, but at every wavelength, right? So you have a blue image, a green image, a yellow image, and a red image. And not actually 4 images, but quasi-continuous. So in hyperspectral imaging, you can actually do that. So for all of these spots now, I took a microscopy image of one of these films with this large PL heterogeneity. And in a moment, I will show you a movie where we are running through these microscopy images from 450 nanometers to 550 nanometers. There will be a lot going on, so I'll let that run twice just to highlight the amount of heterogeneity in this film. So this will repeat now, and you can see hopefully that at low or short wave numbers or short wavelength, you see all the grain boundaries highlighted. So there's emission from the grain boundaries at short wavelengths. Then we go to the main peak where you see this pattern, bright versus dark. And then to longer wavelengths, this pattern does change somewhat. There's still light versus dark. But certainly there are a lot of different areas of emission here in this material. So this thin film is actually very, very complex, and a simple model of one semiconductor does not get us anywhere. Let's stop this here and highlight just on a few aspects. This is now zoomed in. So of course, you need to be lucky that you can actually resolve the grains that you want to look at. So we're looking at 10 micrometer grains. This works now. And we can see that the grain boundaries are really bright at 2.6 eV. And they would also be bright here at 2.5, but the contrast then is a bit lost. This can be lead iodide. So I would think this is lead iodide. We have to check a bit more. But lead iodide emits in this region, and especially if you cool it down, you see this quite pronounced that emission at this short wavelength is due to lead iodide at the grain boundaries. The main peak, of course, we saw that before already, is due to two different grains, but the emission is from all over the grain. And then if you go to this tail of the emission, you can see that actually there are very fine patterns in these grains, right? You can see these lines. We know now from AFM that these are trenches in the thin film. And there are also a lot of little spots. We know now that these are pinholes in the film. So there might, additionally to all the chemical heterogeneity that we observe here, be something of an effect from the outcoupling, so that luminescence can easily, or more easily at least, escape towards the side. Just to come back to the grain-to-grain variation, at room temperature, again, you can already see there are darker grains and there are large areas that are much brighter. Now, if we cool that down, this is 100 Kelvin now, 2.5 eV image. This is the emission of lead iodide. You can see that what is dark at room temperature is very bright in the lead iodide emission region when you cool it down. And if you go to even lower temperature and look at the PL on a semi-logarithmic scale, you can see we have a very pronounced peak here at 2.5 eV. So this is lead iodide. It's definitely here in our thin films, and it seems to be responsible for some of the grain-to-grain variation. Going full circle, so we do not think that this is actually due to variation in the stacking of the inorganic layers, but this is a chemical effect, very likely the lead iodide enrichment in some of the crystallites. Okay, let me summarize what I showed you in the last half hour. First of all, 2D perovskites are bright and tunable emitters. They are rich test bed for excitonic physics. I think they're very interesting from a fundamental point of view, but obviously they can be used for a lot of different devices as well. Shown in the first part, the broad emission bands in these 2D perovskites are due to halide-related defects. And just as a general warning, beware of simplified macro models. Local heterogeneities can determine some of the observed phenomena. In PDMA, lead iodide, for example, I shouldn't have put the two here. We see that there are two distinct crystallites, likely due to local lead iodide enrichment. And with that, I obviously have to thank all my colleagues and collaborators and the funding agencies, DFG and DAAD. So with that, I thank you very much for your attention.